All right, so now let's try to apply some of the properties that we have proved by this point to figure out the limits of certain sequences without resorting to the definition. All right, so let's suppose I want to take a limit of a sequence that I have written on the screen here. And what you see is that we can try to relate that sequence to the properties that were already determined. So the properties that we figured out were, for instance, that if you have a sum of two sequences, then then the limit of the sum of two sequences must be sum of sequences of limits. So I should be able to split this limit into a sum of two limits. Limit n goes to infinity of 5 over square root of n plus limit n goes to infinity 4 times n to the minus 2. Assuming that both limit exists, this is what I get. All right, and then if those two limits exist, then I should be able to factor out a constant outside of a limit. And that means, that's again one of the properties that we proved, that this is the same thing as a 5 times the limit n goes to infinity of 1 over square root of n plus 4 times the limit n goes to infinity. N to the minus 2, actually I can write as 1 over n squared, which I'm going to do here. Again, provided that both limits exist. And in this case, actually both limits certainly do exist, because we proved that the limit of 1 over n to the p, where p is a positive number, when n goes to infinity, is equal to 0. So 1 over square root of n is 1 over n to the power 1/2. 1 over n squared is 1 over n to the power 2. 1/2 and 2 are positive numbers, so that means that both limits are 0. So we have 5 times 0 plus 4 times 0, and of course that is 0. We can do an example like this. So let's make this example 1.5. Let's say I want to take a limit n goes to infinity of 2 times n to the power 1 over n plus 4, let's say 5 to the power 1 over n. So once again, if these limits exist, now in the first example, as I proceed, I use one property at once. But in principle, I can use two properties at once without a problem. So in this case, what I have a limit of a sum of two sequences, and each sequence is multiplied by a constant, right? So that means that if the basic limit exists, if the limits of individual sequences exist, then the limit of a the limit of a linear combination of n to the 1 over n and 5 to the power 1 over n, I can write as twice limit n tends to infinity of n to 1 over n plus 4 times the limit n goes to infinity 5 to the power 1 over n, basically following the same steps that you would use in just a regular calculus course. And then above we show that this limit is 1 and that this limit is 1, and so therefore this is 2 times 1 plus 4 times 1, and the whole thing is equal to 6. All right, so let's do the next example. So what is different here is that As we know, limit of the ratio should be equal to ratio of limits, provided that those limits exist. But in this case, limit of the top certainly is not a finite number. The limit of the bottom, it does not exist either because it's not a finite number, right? Because n squared is a dominant term here, and n squared goes to infinity in both cases, on top and the bottom. So I cannot use a limit of ratio is equal to ratio of limits property. Okay, but then what I can do is I can try to rewrite this in a different way where I should be able to use a ratio of limits property. And the way to do it is to change the expression inside into something, into the ratio of two things that do have a limit. Okay, so how do we do that? Again, this is something that you should remember from calculus. So in this case, what you get is an undetermined form, infinity over infinity, because both top and the bottom go to infinity. How do I get rid of those infinities? I can divide both top and the bottom by the highest power of n, which in this case is going to be n squared. So this is the same thing as 1 over n squared times n squared plus 5n plus 1 divided by 1 over n squared, 2n squared minus n plus 6. Then I can distribute 1 over n squared to get limit n goes to infinity. 1 plus 5 over n plus 1 over n squared divided by 2 minus 1 minus 1 over n plus 6 over n squared. And once I simplify the expression in this form, then now you see that the limit of the top and the limit of the bottom exist. And so now I can use the ratio of limits property. So this would be the same thing as the limit n goes to infinity, 1 plus 5 over n plus 1 over n squared divided by the limit n goes to infinity, 2 minus 1 over n plus 6 over n squared. All right, and here, again, if we somehow stick to showing all steps, what is the limit of the top? Limit of a top consists of the sum of three sequences, and one of those sequences is multiplied by 5, so I should be able to use the property, first of all, that the limit of the sum is the sum of limits, and second, that limit of a constant times a sequence is equal to a constant times the limit of that sequence. So this should be a limit n approaches infinity of 1 plus 5 limits n goes to infinity of 1 over n plus limit n goes to infinity of 1 over n squared, and I'm dividing by something similar. Limit n goes to infinity of 2 minus limit n goes to infinity of 1 over n plus 6 limit n goes to infinity 1 over n squared. And then immediately we see that all limits that we're taking here are of the form limit of 1 over n to the p, where p is a positive number. This limit is 0. This limit is 0. So is this one. And so is that one. And the limit of a constant is at constant, so what we get is 1/2. So if I ask you to do something like this on the test and to explain which properties you are using, then you have to say, again, that the first step, you have an undetermined form. First step, you're simplifying. Second step, you use a property that the limit of the ratio is ratio of limits. Third step, you use properties that the limit of a sum is a sum of limits, and the limit of the constant times a sequence is constant times the limit of that sequence. And then finally, using the property that limit of 1 over n to the p, where p is a positive number, is 0. Let's do another example. Again, this is going to end up being an indeterminate form. Why is it an indeterminate form? Because limit of the first term as n goes to infinity does not exist. It's infinitely large. Limit of a second term when n goes to infinity again doesn't exist. It's infinitely large. But there is a hope that the overall limit might exist because infinity minus infinity, it's not clear what it is. It can be anything you want. It's an undetermined form again. So what do? You do exactly the same thing as I did in the previous example. By the way, at this stage, if you remember your calculus, you remember that the limits of indeterminate forms you can take by using L'Hopital's rule. In this case, at this point at least, we don't know. We assume that we don't know L'Hopital's rule, so you're not allowed to use it. And in principle, you also have to be careful if you try to use L'Hopital's rule. There you have to take a derivative. And if I have a function which depends on n, where n is an integer number, then it's not really even clear what derivative means, right? Because you take derivative of a continuous differentiable function, and in this case, you have a function which is only defined at 1, 2, 3, 4, and it's not defined in between. So strictly speaking, L'Hopital's rule does not make sense for a function like this, the way it is written. All right, so what do we do in the second case? You might remember that the typical procedure again is to simplify, to try to simplify to get rid of a square root. How to get rid of a square root? You multiply and divide by the conjugate. So we have square root of n squared plus n minus n times square root of n squared plus n and divide by the same quantity, square root of n squared plus n plus n. Then we continue simplification, so limit n tends to infinity. On the top now I have n squared plus n minus n squared, right, as a product of the conjugates. And denominator is exactly the same as before. Well, n squared cancels from the top. So what I get is a limit n goes to infinity of n over square root of n squared plus n plus n. Well, n goes to infinity, right? N becomes infinitely large. So n does not have a finite limit. And neither does the denominator because, again, it has n plus something else. So that is not bounded either. So no limit, no finite limit in the denominator. So what do? You continue simplifying. And to continue simplifying, we use now the same idea as I used before. Divide top and the bottom by highest power of n. What's the highest power of n on the top? It's of course 1. What's the highest power of n on the bottom? This term has a power 1. And this term is n squared, but you're taking square roots, so again it's a power 1. So make it a limit as n approaches infinity, n over n times 1 over n times the square root plus n. Okay, now we simplify. N over n, of course, is 1. And what do I have in the bottom? So 1 over n, if I bring it inside the square root, becomes 1 over n squared. So inside the square root, then we have 1 plus 1 over n, and n over n is 1. So that's what we got. Now, limit of the top is 1. Limit of the bottom presumably exists as well. So limit of the ratio is a ratio of limits. Limit as n goes to infinity of 1, or the limit n goes to infinity of square root 1 plus 1 over n plus 1. Limit of 1 is 1. And what do I have in the bottom? Limit of the sum is a sum of limits. So limit n goes to infinity of square root 1 plus 1 over n plus a limit n goes to infinity of 1. We already used an example where we said that the limit of a square root of a sequence, so we proved that the limit of a square root of a sequence is square root of a limit of that sequence. So this should be the same as 1 over square root limit 1 plus 1 over n as n goes to infinity. Right, that's again an example from a previous section, plus a limit, the limit n goes to infinity of 1. And this limit down here is a limit n goes to infinity of 1 plus a limit n goes to infinity of 1 over n. Limit of 1 is 1. Limit of 1 over n, that's like a limit of 1 over n to the p again, with p equal to 1, and that limit is 0. And so at the end of the day, this is going to be 1 over square root of 1 plus 1, so the limit is 1/2. Okay, so that means that by using the properties, I should be able to find the limit like this. And so on the next test, I would expect you to do what I just did, find the limit, and explain every step by properties of a limit that you use on that step. And now let's move on to the next topic. It's still a part of the same section, which is related to what we're just talking about. When I have a sequence which is increasing in an unbounded fashion, right? So then I know that that sequence does not have a finite limit, but I can define then, or try to define, what I mean by an infinite limit, because still the sequence is following the certain trend, right? It increases without a bound. So we're going to give the following definition. We're going to say that the sequence Sn converges to infinity if, now what does it mean that the sequence converges to infinity? It means that the terms of that sequence are going to become arbitrarily large if the index n becomes large. What does it mean that the sequence can become, the elements can become arbitrarily large? They're going to exceed any number that you choose eventually, right? Okay, so then the sequence goes to infinity if for any m greater than 0, there exists a threshold n in R such that if n is bigger than capital N, then Sn is greater than m, right? Such that Sn is bigger than m if n is greater than capital N. So in this case, we say we're going to write actually limit n goes to infinity of Sn is equal to infinity. I hope that this makes sense. I hope it makes sense that the previous definition of a limit is not going to work in this case the way we wrote it, right? Because the previous definition of a limit said, or actually, let's see if we can use a previous definition of a limit here. So limit n goes to infinity of Sn equal to infinity. If I just stick to that previous definition, then I would have to say if for every epsilon greater than 0, there exists a capital N in R such that Sn minus infinity is less than epsilon if n is bigger than capital N. But of course, this does make sense because this expression does not make sense. And why it doesn't make sense? Because I cannot add anything to infinity. Infinity is not a number, right? So I have to come up with a different definition, which I just wrote to you, right? So what does it mean that you get close to infinity? It doesn't mean that Sn minus infinity is less than epsilon. It simply means that Sn eventually will exceed any positive number that you prescribe. In fact, it would exceed any number that you prescribe, but we'll stick to saying positive numbers. Okay, and so this I can extend to include the case of minus infinity. So that will be the second definition. Limit is going to be minus infinity. In what case? If the elements of my sequence can become as small as not as small, but as negative as I wish, provided that n is sufficiently big. So then in this case, if I pick any m which is less than 0, then there will exist n and r in R such that what happens now? Sn is arbitrarily large and negative, so Sn must be not larger than m, but smaller than m, right? If n is bigger than capital N. And in this case, then we'll write that the limit of Sn is equal to minus infinity. And so now what we get would be that the limit can be, of a sequence can be a finite number, it can be infinity, and it can be a minus infinity. All right, and then in the next lecture, we're going to give some examples and discover some of the properties of infinite limits.